Welcome back to Practical Electronics and Circuits 101. In today's episode, I'll be giving an introduction to transistors, and we'll be showing how to properly use them in your projects, so this will be one you'll definitely want to watch all the way through. Before I start, I also want to mention that the full playlist is in the video description in case you're a first-time viewer and want to get caught up with the previous videos. Now let's begin by talking about what transistors are and the different applications they're used for. And then afterwards I have a few hands-on examples showing how to power various devices, including lights and DC motors. So from a fundamental point of view, transistors are simply an electronic switch made from semiconductors that can be used to turn on and turn off other devices, or to amplify a signal. Before transistors were developed, vacuum tubes were used to accomplish these tasks. But the drawbacks of tubes is that they're large, waste lots of power, and as a result, they get quite hot. Since transistors are made from semiconductors, they don't suffer from these issues nearly as much as tubes do, which is why transistors and semiconductors in general have become so widely adopted and have been the driving force behind the electronics revolution which society has experienced over the last several decades. So let's start by going over how a simple NPN transistor can be used as a switch. I'll go into more detail soon on what NPN means, but for now, let's just say this is a very basic transistor. Now the majority of transistors have 3 pins. In this case, we have the emitter as the first pin, the base as the second pin, and the collector as the third pin. Now let's imagine we connect the collector to the positive rail of a 12-volt power supply, and we connect the emitter to ground. If we were to make an analogy, we can imagine the current flowing through the transistor as water, in which case the transistor itself can be thought of as a valve that can either open to allow the water to flow, or it can close to stop the water from flowing. This valve is controlled by the base, and we can control the base by feeding a signal to it. If we supply a high signal to the base, then it will open up the valve and allow the current to flow. But if we give the base a low signal, or in other words 0 volts, then it will close the valve and the current will stop flowing. Now if we connect a load in this current's path, for example, let's say we connect a 12-volt LED strip, you can see how we can now control this LED strip with the transistor. This is useful because we can now control the LED with a signal that's much lower power than what the LED strip requires to operate. In most cases, this signal will usually come from a microcontroller. Microcontrollers contain a number of input and output pins, and the output pins can be used to control other devices. It turns out the output pins are actually tiny transistors themselves, but most of them are only capable of outputting up to 5 volts, and each pin is only capable of supplying up to around 10 or 20 milliamps, depending on the particular microcontroller. In other words, these output pins are extremely low power and aren't meant to power devices, but rather they're just meant for communicating with sensors and other microcontrollers, or to activate larger external transistors, which will then be responsible for supplying the power to whatever device needs to be powered, such as lights, motors, relays, and countless other devices. This was a simple example of how a transistor can be used as a switch, and I'll be showing a few hands-on examples similar to this one later on. But let's first go over some of the other applications that transistors are commonly used for. Let's now look at a schematic for a simple guitar boost pedal. In case you're not familiar with guitar pedals, a boost pedal is used to increase the volume of a guitar signal before it goes into the amplifier. A typical electric guitar pickup will only output a few hundred millivolts, which isn't much, but a boost pedal can be used to amplify the signal up to at least several volts. In this example, the transistor is connected to a 9-volt power rail, and the guitar signal is fed into the transistor's base. Now I won't be getting into every detail in this video of why these particular resistor and capacitor values were chosen, but in a nutshell, The resistor values are chosen to set the correct bias so that the conditions are optimal for this particular transistor, and the capacitors are here to decouple the pedal from its input and output, and also to create filters with the nearby resistors. But anyway, the purpose of this example is to show that all the transistor is doing is amplifying the guitar signal. The transistor controls the signal that's flowing down from the 9-volt power rail, which also happens to lead to the output of the pedal. So let's say the guitar is producing a signal that has a peak-to-peak voltage of around 200 millivolts. The transistor will replicate the guitar signal, except the new signal will have a peak-to-peak voltage of up to around 9 volts, since we have a 9-volt power supply in this example. It'll actually be a bit less than 9 volts, but anyway, this boosted signal will also go down this path to the output, where we have a pot that acts as the volume control. As I went over in a previous video, pots are simply a voltage divider. So when the pot is turned all the way up, it simply passes the full signal from the transistor to the output jack. And when the pot is turned down, it will create a voltage divider that trims down the voltage before it gets sent to the output jack. Now, another area where transistors are used is in computational logic. Transistors are a fundamental component in computers. I'm sure many of you have heard how modern CPUs contain at least several billion transistors. But these transistors aren't meant to provide a lot of power or to amplify signals, but rather their function is simply to provide a signal that represents information in the form of a 1 or a 0, or on or off. Now, computer architecture isn't super useful for the sorts of projects I plan to do on the channel in the upcoming year, but perhaps at some point in the future I'll make a more detailed video on computer engineering in case anyone is interested in how CPUs work at a fundamental level. But in a nutshell, several transistors can be used to create what's known as a logic gate. These gates include operators such as AND, OR, NOT, and several others. If you've ever taken a philosophy class, then you should already be familiar with these logic operators and expressions. It turns out the exact same concepts also apply to computers. Engineers create truth tables of how they want their system to react to certain inputs. Then they transfer that logical expression into hardware by using logic gates. Mathematical operations such as addition and multiplication can also be built with a large array of logic gates. This is barely scratching the surface of how computers work, but hopefully at least you now have a general idea of the role transistors play in computers. They're there to build logic gates. So now let's talk about some of the different types of transistors, and then afterwards I'll show a few hands-on examples. Now, there's actually many different types of transistors, but the ones you see here are by far the most common types of transistors that you'll encounter. BJT stands for bipolar junction transistors, and these are the most basic types of transistors. The other type I'll be talking about are FETs, which stands for field effect transistor, and these offer a number of advantages over BJTs. However, they're more expensive to manufacture, which is one reason why BJTs are still used today. The main advantage FETs offer are better efficiency, lower noise, and smaller physical size. Another major difference is that BJTs are current-controlled devices, while FETs are voltage-controlled. So the way they operate is very different from each other, and circuits need to be specifically designed for one or the other. The two most common types of FETs are JFETs and MOSFETs. JFETs have better properties for low noise environments, so they're commonly found in audio applications. However, JFETs are more expensive to produce than MOSFETs, and with the exception of noise, MOSFETs have better properties for most applications, which is why MOSFETs are more common than JFETs. Now, as far as construction goes, BJTs are simpler in design. In a previous video, I gave an introduction to semiconductors and used diodes as an example, Since they're the most simple component made from semiconductors, diodes contain a single p-type semiconductor and a single n-type semiconductor, which has an effect where the current is only allowed to flow in one direction. Well, a BJT's design is extremely similar to this, except there's a third semiconductor added. An NPN transistor has a single p-type semiconductor sandwiched in between two n-type semiconductors. A PNP transistor, on the other hand, has a single n-type semiconductor sandwiched in between two p-type semiconductors. The main difference between these is the direction the current is allowed to flow. An NPN transistor allows the current to flow into what's referred to as the collector, and exits the other side, which is referred to as the emitter. On the other hand, a PNP transistor allows the current to flow in the opposite direction, where the current enters the emitter and exits the collector. The semiconductor in the middle is referred to as the base, and this is what activates the transistor. NPN transistors are activated by a high signal and deactivated with a low signal, as you'd expect. But PNP transistors are the opposite, where a low signal activates it while a high signal will make it block the current. This means that these two types of transistors can't be swapped with each other. A damaged NPN transistor needs to be replaced by another NPN, not a PNP, unless the circuit is designed to accommodate a PNP. Now, FETs on the other hand have a slightly more sophisticated design. Here we can see a comparison between a BJT NPN transistor and a MOSFET. The BJT has the p-type semiconductor sandwiched in between two n-types, just like we saw before. But notice how the MOSFET's construction is much different. Also, the MOSFET's pins have different names. Instead of a collector, emitter, and base, the MOSFET has a source, drain, and gate. But just like BJTs, MOSFETs can be made to be either N-type or P-type, which will determine which direction the current is allowed to flow. The gate is what controls the MOSFET, similar to how the base controls a BJT. Different types of transistors also have different schematic symbols. So now let's do a couple hands-on demos. I'll be showing two simple circuits today. The first uses a 2N3904 transistor, which is an extremely common BJT NPN type, and we'll be using this to power 4 red LEDs. The second example will use a high-power MOSFET transistor and a brushed DC motor. I'll leave a link in the video description for a transistor kit on Amazon that comes with a variety of transistors, including the 2N3904. I'll also leave a link to the IRF3205 MOSFET that I'll be using in the second example. Now, I'll be using a Raspberry Pi that's running a simple Python program to control both of these circuits. The Python program simply turns the output on and off every second. In other words, the output will be on for 1 second, then it will be off for 1 second, and then it will continue to cycle indefinitely until I stop the program. I'll go into more detail on how to set up the Raspberry Pi in another video, but for now, all we need to know about the Pi is that its pins output 3.3 volts and are only capable of supplying about 16 milliamps, which isn't nearly enough current to drive these 4 LEDs, much less a DC motor, which is why transistors are necessary. Now the Raspberry Pi provides two power rails, a 5V and 3.3V rail. The 5V rail is directly connected to the Pi's power supply, so the maximum current that's available entirely depends on your particular power supply. I'm using this phone charger which can provide up to 2 amps. Now this Raspberry Pi is actually the original Model B, which is ancient by today's standards, but one nice thing about it is that it doesn't use much power. At the most it uses up to 1 amp. Since this power supply can provide up to 2 amps, that means we have about 1 amp left over to power other devices, which is more than enough to power these 4 LEDs. So for this example, I won't be using an external power supply. I'll be using the Raspberry Pi's 5-volt power rail to power the transistor and LEDs. Alright, so the first thing we need to do is figure out how much current these LEDs will be using. Now I have 4 LEDs here that are all the same type and color, which means I can get away with just a single current limiting resistor. If these were different colors, then you would need separate resistors for each one, since they have different forward voltages. So now 4 LEDs will use approximately 80 milliamps at maximum brightness. So let's aim for that. With a 5-volt power source, we would need roughly a 40 ohm resistor to achieve 80 milliamps. So that's what I have here is roughly 40 ohms. Now let's take a look at the datasheet for this 2N3904 transistor. Now there's quite a few specs here. Most of these we don't really need to know, but there are a few important ones that you'll definitely need to keep in mind when designing a circuit. So the maximum voltage the transistor can handle is an important one. The collector base voltage maximum is 60 volts. Collector emitter voltage maximum is 40. So we're not using anywhere near 40 volts. We're only sending 5 volts through this transistor. You know, a lot of this stuff is irrelevant for what we're doing unless you're an engineer designing something extremely specific. I'd say the two most important specs are the collector current, uh, the peak current, and the total power dissipation. So again, we're only going to be using around 80 milliamps, which is much less than the 200 milliamps collector current. But the more important spec here is the total power dissipation, which is only 500 milliwatts. So remember, power is a product of current and voltage. So 500 milliwatts means that if we were to draw 200 milliamps, we would only be able to do that with 2.5 volts. All right. So the more voltage you feed, the less current you'll be able to get out of it. So, if we were putting, let's say, 10 volts through this transistor, which by the way is very physically small, like probably you can't see it very well on the video, but of course, I'll include a schematic and edit it onto the video so you can clearly see how to connect all this. But anyway, so back to what I was saying about the power dissipation. At 10 volts, you're only going to be able to get 50 milliamps out of this thing. So the total power dissipation is the important spec to really pay attention to when it comes to your limit. All right. Now, the other thing we need to pay attention to is this section here, DC current gain. So, depending on how much current we're demanding from the transistor, its gain will be dependent on that. And what this tells us is basically the amount of current that we feed into the base from the Raspberry Pi's output pin will be multiplied by a factor, its gain, which will determine the current that the transistor can provide. So we require 80 milliamps. So let's actually round that to 75 milliamps because that's right in the middle of 50 and 100. So at 50 milliamps, we get 60 gain. At 100 milliamps, we get 30 gain. We're right in the middle of this, so we'll be getting a gain of 45. All right? So that means that however much current that the Raspberry Pi pin is supplying the base will be multiplied by 45 to determine the total current that the transistor is providing. So since we want approximately 80 milliamps, we divide that, or 75 milliamps, close enough. We divide that by 45, which means that the Raspberry Pi's output pin will need to provide about 1.7 milliamps, which is much less than its maximum of 16 milliamps. So that's good. We don't want to get close to the maximum rating of the pin. Using Ohm's law and knowing that the Pi is outputting 3.3 volts on its output pins, we can use Ohm's law to determine we need a resistor value of roughly 1941. So that'll be the resistor going into the transistor's base. Now the resistor I have here is actually a bit more. It's 2.2 kilo ohms. The value isn't crucial. As long as you're in the ballpark, it should work fine. Since I'm using a higher resistor value, that will result in slightly less current going through the LEDs, but that it's a very slight decrease in brightness. So I already have the Pi outputting, the program is running. So all I need to do is take this wire that's coming from the Pi's output pin, and I'll connect it here to this resistor going into the transistor's base. And see, it's blinking just like I said. It stays on for 1 second, turns off for 1 second, and it repeats the cycle. All right? So now we can move on to the next example, which will use this big 24-volt DC motor here. We won't be running it with 24 volts. We'll be running it with less voltage, and that means that the motor will just be turning slower. It'll still work fine. So the transistor we'll be using is this one here. This is a MOSFET. It's the exact model is an IRF 3205, I believe. Now this is a high power MOSFET. Like this is the type of MOSFET you'd see in a power supply. This thing can deliver like 100 amps and up to I think something like 300 watts or 200 watts, excuse me. But of course, to get that much power out of it, you need to attach a large heat sink to it. Today, we are barely running like at the most half an amp. So we don't need a heat sink in this case. MOSFETs are very efficient, which is why it can do that in such a small package. Now, I wanted to point out that using a transistor to power a DC motor is completely fine, but it's not ideal because you can't change direction. You can only turn the motor one direction with this current setup. Now, you could design a more complex circuit that uses multiple transistors in order to get the ability to reverse direction, but that's more work than you need to do. Ideally, you'll want to get what's called an H bridge, which contains that circuit inside it. It takes care of everything, has protection diodes, and all you need to do is connect the motor to it, connect your power supply, and connect the control pins. And that using an H bridge is the ideal way to control a motor. And I'll probably be doing another video sometime in the future on H bridges. But for now, this is a very simple example. You can only turn the motor in one direction with this. Now, a few other things to note is MOSFETs are voltage controlled, as opposed to this previous example with a BJT, which is current controlled. So, with the MOSFET, it doesn't matter how much current the Raspberry Pi pin can provide. All that it cares about is seeing a certain threshold of a voltage, which in this case, I believe this MOSFET has an activation gate threshold voltage of 2 volts and max 4 volts. So any voltage between 2 and 4 volts will activate this MOSFET and it will deliver whatever power the load requires. All it cares about is seeing that a certain voltage from the control pin. Now the thing about being voltage controlled, if you were to run into a scenario where the motor and transistor still has power, but the Raspberry Pi loses power, when a microcontroller loses power, it can get into a state where its output pins will float, which means there will be a very tiny current, but there will still be a voltage coming out of the pins, even if the microcontroller doesn't have power, which means that that can activate the MOSFET. And if you are, uh, if you have a motor connected to that MOSFET, depending on what you're using the motor for, that could be potentially dangerous. If the motor is big and turning some device that's moving around, the last thing you want is for that thing to be turning on and off randomly without warning. So, for that reason, we have two resistors here going into the gate. One resistor, this is a 10K resistor, is going straight to ground. And then we have another resistor, which is a 1 kilo ohm, which is where I'll be connecting the control pin to. So what this does is, if there's no input coming from the 1K resistor, then the 10K resistor is going to ground the gate, meaning it's guaranteed to be 0 volts, and we don't have to worry about the motor turning on and off randomly if there was a problem with the Raspberry Pi. Okay, so yeah, that you'll probably want to do this with all MOSFETs, just to ensure that you don't have any unexpected, things happening. Now, the other thing that is important here is this diode. So, as I talked about in a previous video, coils create a magnetic field. When something that has a coil is being powered and then the power turns off, that magnetic field will collapse around the coil and it will send a current through the circuit. So, anytime you're powering a device with a coil, you'll need to make sure you include a diode so that it protects the transistor and the rest of the circuit from what's called flyback voltage or freewheeling. There's a few names for it, but yeah, again, so anytime you use something with a coil, you'll need to make sure you include a diode here that runs in parallel with the load to protect the transistor from that. All right, so now we can turn this on. And oh yeah, so it only draws about 200 milliamps when running at 5 volts. The higher the voltage, the more current it will draw. Now, since it only draws around 200 milliamps at 5 volts, I can actually power this with the Raspberry Pi's power supply. So that's what I'll do first, and then afterwards I'll use a different power supply running at 12 volts so we can get, it'll drive the motor faster. So that way you can see how to use two power supplies on a single circuit. Alright, so I'll disconnect the Raspberry Pi's output pin from the LEDs and connect it to this one here. And see, now we have the motor reacting at the same rate as our LEDs were. Um, so yeah, let's now use a second power supply, a more powerful power supply that can deliver 12 volts and enough current. So when connecting a second power supply, it's very important to disconnect the Pi's power rail. The 5-volt power rail that we have powering this circuit needs to be disconnected, but you need to keep the ground connected. The Pi and the rest of the circuit need to have a reference so that they're in agreement with voltages. So it's very important that you keep the ground connected from the Pi, but you disconnect the power rail when connecting a second power supply. So that's what I'll do now. I have the second power supply here, and I'm gonna just connect this pin over here, which will keep it out of the way. Okay, so the power supply is connected. So now I'll go ahead and turn on the power supply, which is supplying the transistor 12 volts. So now when I reconnect the control pin, we should see the motor spin a lot faster. Yeah. So you can see this is spinning quite a bit faster now. So yeah, that pretty much wraps up what I hadn't planned today. Like I said before, this is just an introduction. Obviously, there's a ton more to talk about regarding transistors, and if you looked at the data sheets for these, there's just a ton of different specs. There are countless different transistors that some have very slight variations in these specs. Some of them are very different specs. So I think the stuff I showed today should serve as a good introduction so that you can at least build some straightforward circuits like I showed today. And of course, in future videos, when I start some projects using these concepts, I'll go into more in depth as the project requires. But anyway, so yeah, I'll be starting some projects very soon, and of course, the channel won't be limited to just electronics projects. I have a bunch of other projects planned as well, but just bear with me and I'll be coming back to this stuff very soon. If you found this video to be helpful or informative, then be sure to give it a thumbs up. And also, if you haven't subscribed to the channel yet, then doing so would be extremely helpful. As always, thanks for watching, and I'll see you guys in the next one.